Hey everyone, this is the how to do the calculations for your solute potential lab setup. Now, the lab setup itself is in the question. You are given some background information about how we did this lab. Now we're going to look at the data and how to do the calculations. In order to understand what we're doing, we're looking at water potential. So water potential, let's focus on the picture that is provided for you over here. This is something that applies to plants because plants have a cell wall that allows them or prevents them from bursting when placed in a hypotonic solution. As more and more water enters into the cell, through the process of osmosis, the water in the cell and the water filling up that central vacuole begins to exert pressure on the cell wall. The arrows in blue show the pressure that the water is placing or pushing against the cell wall. And what happens is, as the cell begins to fill up, eventually the cell wall will not stretch anymore and begins to push back on the water. I'm going to do those arrows in red. And so the pressure that the cell wall is pushing back when it's reached its stretching point, its maximum pressure, that pressure is known as water potential. Water potential can be calculated by adding the solute potential and the pressure potential. This Greek letter right here that kind of looks like a pitchfork is the Greek letter psi, P-S-I, and that represents your water potential. So your water potential is equal to the solute potential plus the pressure potential. Now there is a hack, something that we can do to make this process a lot easier on ourselves. And that is this: when in an open system, such as a cell, when there is no external covering here that is exerting pressure other than the air and the environment that the cell is in, it is considered an open system, and our pressure potential here is equal to 0. That means, to make this simpler, we can ignore this portion of our equation because this value here is going to be equal to 0. So what we have is that our water potential is equal to the solute potential, and the solute potential is something that we can calculate. Again, that water pressure is just the pressure that water will exert on another solution. And for our cells, it's the pressure on the cell walls. Water will always move from solutions of higher water potential, higher pressure, to solutions of lower water potential, lower pressure. Water potential determines the direction of the water movement. So now that you know or have an idea of what the water potential is, in other words, the pressure that the water is putting on the cell wall of a plant cell when the plant cell is full due to water coming in on a hypotonic solution, it's that pressure. We look at what and how to calculate that value. So your water potential is that pressure. So how do you calculate it? Well, in order to calculate it, you need to know the solute potential. And that can be done using an equation. But in order to figure out or solve the equation, we need to understand at what point does water coming into the cell fill up that central vacuole to the point where the cell walls get stretched and then can no longer hold any more water, and the cell wall pushes back against the water. And that is what our data set is for, is to help us see at what concentration is there enough water coming in that the cell wall will begin to push back and not allow any more water into the cell. So here's how we're going to do that calculation. First, you're going to need some graph paper or grid paper. You're also going to need numbers provided to you from the lab itself. I'm going to start by creating my axes and explaining what they mean. Let's start with the y-axis. The percent change is my y-axis, and we're going to start at the concentration of 0, where there is no change in the mass of your object. Any percent change that is positive means that your potato piece or root vegetable piece, whatever it is, gained water. That is why it is heavier at the end of the experiment than at the beginning. And so the percent change above zero or positive is where there was a net influx or input of water into the cells. Now I'm putting just a general trend of gained water, but up here you would need to scale your values based on the numbers that you were given. So all of these values right here should be scaled positive values to the maximum number you are going to need to graph on this chart. Any values below this line right here represent a loss of water from the cells to the beaker. So water left the cells in this portion down here. And again, you're going to need to scale your grid here based on the values that you were given. This means that the values over here represented when the solution was hypotonic to your potatoes, and these values right here represent when the values were hypertonic to your potatoes. And this line right here represents no change in the mass of the potatoes. Now that I have the y-axis labeled and drawn, and again, you should have actual values here based on the values that you were given for the lab, we're going to go ahead and put the x-axis in. Now the x-axis is going to be the molarity of the solutions. Okay, I've gone ahead and scaled my x-axis. I have enough space here that I can put 5 grids or 5 squares, 1, 2, 3, 4, 5, in between each value. And this will help you out tremendously on getting the information we need from this graph. So if you can, go ahead and put 5 squares in between each molarity. And again, that will help you. So now what you're going to do is you are going to do a scatter plot. In other words, you are going to put dots at each of the molarities and what that percent change was. Now this is different for each student, so I'm going to just draw general labels or general plots that aren't anywhere specific. Yours are going to be in different locations based on what the percent change was at each of these molarities. So I would look up at my table and I would see at 0 molarity what was the percent change, and I would put a dot along the y-axis wherever that change occurred. Keep in mind that for this video and for this example, I'm not using specific numbers, but you do have specific numbers you need to be using for your calculations. Please use the lab data to figure out what your numbers are. Now I'm going to go to point 2 and I'm going to plot that data point. And I will do the same at point 4, at point 6, at point 8, and at 1. Now that I have all my dots plotted, again, based on the molarity and the results of your specific lab data, what we're going to do is we're going to add a line of best fit. Your line of best fit should try to go in between and as close to as many of your points as possible. There is going to be some variation in how you draw this, and so I do recommend you use a straight edge or a ruler to try to get as straight as line as possible. Once you have your line of best fit, what you want to do is identify the spot where this line of best fit crosses the 0% change. So here is my 0% change, and we're going to follow along until we see where it crosses or where that line of best fit crosses that point. That concentration looks to be about 0.405. Keep in mind that the way that you drew your best fit line is also going to affect where this value is. So there is a little bit of wiggle room in the in the answer keys when it comes to drawing a line of best fit, because it depends on how you draw that line of best fit. This number 0.405 is necessary for calculating the solute potential. So let's talk about how to do that part. So to calculate the water potential, based on the previous slide, I'm going to remind you that the water potential is equal to the solute potential. We can ignore the pressure potential because for cells, these are considered open systems, so our pressure potential is equal to 0. Luckily, all of this information is available for you on the formula sheet. So let's take a look at that solute potential and how to calculate that value. Once we know the solute potential, we will automatically know the water potential. So this is the equation for solute potential. You'll notice a couple of things. Number one, that it is a negative value. So please be very careful when you're reporting the solute potential, because if you don't report it as negative, it will be counted wrong. There are 4 different variables in this equation, and all you have to do is plug in the value for each of these variables and you will get your solute potential. It's algebra, and it's very easy since most of these values are given to you. I represents the ionization constant. This will always be given to you in a problem. The only time it's not given to you is when you're looking at sucrose. Fortunately, sucrose has an ionization constant of 1, and that information is on your formula sheet. So I'm going to rewrite this equation using the values given or known to us. In this lab, we were using sucrose, and so this value for your ionization constant is equal to 1. C, this is the hard part for students. This is the tricky part for students, so I'm going to highlight it. The reason that it's hard for students is because they forget what that is. And when you look it up on the formula sheet, all it tells you is that C is the molar concentration, but it doesn't tell you which molar concentration. So please make a note to yourself so that you don't fall into this trap and that it's easy for you. C represents the concentration where there was no change in the potatoes. On this example, it is 0.045. It is wherever your best fit line crosses that 0% change. That is the hard part for students to remember. That's the only value we use, is where that line of best fit crosses that 0% change. R represents a pressure constant. It is given to you on the formula sheet. For simplicity's sake, I'm not going to include any values or any units to keep the numbers as clean as possible. T represents the temperature, but be careful because this is the temperature in Kelvin. If you don't know how to convert to Kelvin, please look at the formula sheet as that information is given to you. The temperature that the lab was conducted at is also given to you in your background data. So I'm not going to enter any value here because my number will be different than yours. That represents the temperature in Celsius, and to convert to Kelvin, we add 273. Once you have figured out what that temperature is, all you need to do is just type this entire equation into your calculator and you will get your solute potential. And that's it. So now that you have your solute potential, you know the water potential, which again is the pressure that is being exerted by the cell walls of a plant cells when placed in a hypotonic solution. I hope this video was helpful to you guys. Thank you so much for watching.